All right, time for a brand new topic, rings. So here's the definition of a ring. A ring, R, is a set with two binary operations. We usually denote the binary operations as plus and times, but they could be absolutely arbitrary binary operations that take two elements in R and give you back an element in R, such that the following holds. Condition 1. R with the plus operation is an abelian group. So the plus operation is commutative. It has an identity. We're going to let 0 be the identity. And it has inverses, meaning I could do subtraction. Condition 2 for a ring. The multiplication is associative. Condition 3. There's like a distributive property with the relationship between multiplication and addition. So multiplication distributes over addition. Now, multiplication is a binary operation that may not be commutative, so I want the distributive property to hold regardless the order of multiplication. And this has to be true for all A, B, C in the ring. I'm going to put an optional condition, condition 4, that's not always in the definition of ring, but for our course, I'm going to make it part of the definition. I'm going to say that the multiplication binary operation has an identity, which we'll denote as 1. So what I mean by that is there's a 1 in the ring such that A times 1 is the same as 1 times A, and that's just A. So some people might say that our definition of ring is a ring with unity. So this is with unity, meaning that I have the number 1 in my ring. Okay, what are some examples? The best example of a ring, and if you ever get confused about rings, go back to this example and see if your statement or condition is true for this ring, since it's the best possible example. Z. Z with the usual plus and times. That's a ring. Why? Addition of integers forms an abelian group. There's a 0. There's inverses, meaning I have negative numbers. It's commutative operation. There's a multiplication. I could multiply two integers. That's an associative operation that satisfies this distributive property. And it has a 1. What it does not have, what the integers do not have, are multiplicative inverses. So there may not be multiplicative inverses. That's okay. It's still a ring. You could do Zn with addition and multiplication calculated mod n. That also is a ring. I can add two numbers mod n, I can subtract them, and I can multiply, but I may not be able to divide necessarily. Both of these examples are commutative rings. These are commutative rings because the multiplication is commutative. But if I look at n by n matrices with entries in the complex numbers, with the usual addition and multiplication of matrices. This is a ring. I can add two matrices, I can subtract two matrices, and I can multiply two n by n square matrices together. That's fine. But this is a non-commutative ring because the multiplication is not commutative. Here's another example. Let R be any ring. Then you could do this. You could form all polynomials with entries coefficients in R. So this is the set of all polynomials of the form like an x to the n down to a1 x to the first plus a0, where n is a non-negative integer and the coefficients are in my ring. This is a polynomial ring. It's a perfectly valid ring. I can add two polynomials together in the way that you learned in high school. You could subtract two, and you can multiply two by expanding everything out using the distributive properties. So that also is a ring. It has a 0, the polynomial where all the coefficients are 0. It has a multiplicative identity where all the coefficients are 0 except for this last one, which is 1. So that's a ring. I'd like to do one more, maybe more exotic example of a ring, the quaternions. So here's a more interesting novel example. I'm going to let I hat, j hat, and k hat be three indeterminants or vectors where they satisfy this condition. I squared, imagine I is the complex number, the imaginary I. I squared is going to equal -1, but I'm going to also demand that of j squared and k squared. And if I multiply I, j, and k in this order, I also get -1. So I'm going to say that I squared, j squared, k squared is -1, just like the complex numbers. And also I, j, k is -1. We saw this example very briefly last quarter, where if I take plus or minus 1, plus or minus I, plus or minus j, and plus or minus k, this forms a non-abelian group of size 8. So it's the only other non-abelian group of 8 elements besides the dihedral group. But this time I'm going to use the quaternions to form a ring. So I have these things, I, j, and k, that satisfy this condition. My ring is going to be all real numbers, coefficients of polynomials in 1, I, j, and k. So when I put this bracket here, that notation means form all possible polynomials, just like I did in one variable here, all possible polynomials in 1, I, j, and k with coefficients in R. So if I were going to write that down as a set, it would look like a0 times 1 plus a1 times I plus a2 times j plus a3 times k, where a0, a1, a2, and a3 are in the reals. This is a ring. This is a ring. You can add two of these together. You could treat these coefficients as elements in a vector. So you can add two elements in this set component-wise, and you can multiply. You can multiply the same way that you multiply polynomials using this property here. So for example, for instance, let me take two elements in this set. Maybe I'll do 1 plus 2i, and I'll multiply that by 1 plus 3j. So you'd multiply the way you multiply polynomials usually. I'd get 1 plus 2i hat plus 3j hat. And then I think I'd get 6i hat j hat. What is I hat j hat? Well, I can get this by looking at the condition right here. To find I hat j hat, I could look at this condition and multiply both sides on the right by k hat. So if I take that condition and I multiply on the right by k hat, I get I hat j hat k. K equals negative k. So I multiplied by k on the right. But this condition says k squared is negative 1. So that says I j negative 1 is negative k hat. So I can multiply by negative 1 and I could find ij is k. So in the end I get 1 plus 2i hat plus 3j hat plus 6 k hat. So here's an example of a ring that's maybe not as obvious as the usual ones: Z, Zn, matrices, and polynomials. These are the four big examples. We'll revisit them as the quarter goes on. All right, great.